The hypoxic insert device has 6 pillars that nest into the wells of a 6-well plate. Gas flows across the microfluidic network at the base of the pillar and can diffuse across the gas-permeable PDMS membrane separating the gas network and culture media. This device minimizes the diffusion path length between the oxygen source, the microfluidic network at the base of the pillar, and the cells, permitting more rapid oxygen concentration equilibration. The device also permits far greater control over the spatial pattern of oxygen exposed to cells, which is determined by the microfluidic gas network design made by standard photolithography using photomasks.
Hi, I'm Sean Opegard from the Dr. David Eddington Lab in the Department of Bioengineering at the University of Illinois at Chicago.
Hi, I'm Ellie Sinkawa, also from the Eddington Lab.
Today we will show you how to fabricate, validate, and utilize a custom device to expose in vitro cell cultures in a 6-well plate to different oxygen concentrations.
We use this procedure in our laboratory to study the effect of oxygen on wound healing, reactive oxygen species generation, and migration. So let's get started.
To begin fabrication of the oxygenating insert, prepare polydimethylsiloxane, or PDMS, in a 10:1 ratio between prepolymer and curing agent, according to manufacturer's instructions. The PDMS mixture is added to a previously machined Delran mold, patterned to mimic the shape of a standard 6-well culture plate. Once cured at 75 degrees Celsius overnight, the resultant replica molded pillar array will form the first of 3 components that comprise the oxygenating insert. In order to fabricate the second key component of the oxygenating insert, an SU8 master is prepared by first spinning SU8 2150 on a silicon wafer. A photomask is applied to the wafer, and the SU8 is exposed to UV through the photomask to create a master mold with a microchannel thickness of 300 micrometers. Pour PDMS on top of the SU8 master and cure for 2 hours at 75 degrees Celsius to yield a positive mold, which will ultimately form the microchannels at the bottom of each pillar. The third component of the device is fabricated by spinning PDMS on a silicon wafer at 500 RPMs for 10 seconds, followed by 900 RPMs for 30 seconds, to achieve a 100 micrometer thick membrane. As PDMS is gas permeable, oxygen can be delivered into the microchannels directly through this membrane. Once all components are prepared, each bonding surface is subjected to oxygen plasma treatment for 1 minute using a handheld plasma device. First, bond the 6 microchannel components to the pillar array. Then, puncture 2 holes in each pillar to serve as the gas inlets and outlets. Finally, bond the membrane to the bottom of the microchannel. To facilitate bonding and expel any bubbles, the plasma-treated surfaces are pressed together for about a minute using the blunt end of a pair of tweezers. Wait 1 hour between each bonding to ensure the device is completely bonded and can be calibrated. Once a complete device has been fabricated, the level of oxygen received by cells when using the oxygenating insert in actual experiments needs to be calibrated. For calibration, use a fluorescent oxygen sensor, or FOXy slide, which contains a fluorescent ruthenium dye coating that is quenched by oxygen. FOXy slides are pre-cut to fit into the bottom of a 6-well plate. The FOXy slide should be cut to cover as much as possible of the well surface. Since the FOXy slide has a thickness of about 1 mm, modify the device to maintain the desired distance for adequate membrane slide diffusion. This distance depends on the experiment, but for most cases should be below 1 mm. Using the handheld plasma device, bond 4 cut 1 mm thick glass microscope slide posts of roughly 6 mm in length and 4 mm in width to the bottom of the device. The device will rest on posts atop the slide. Cut glass cover slips can also be used for a diffusion gap of 0.17 mm. To validate oxygen usage, add 3 milliliters of deionized water at room temperature into the wells of the 6-well plate where the oxygen will be measured. Place the device in the plate and using Metamorph software, select the number and location of the desired positions on the Foxy sensor slide to assay oxygen concentrations. Connect Tygon tubing between the oxygen gas tank and the hypoxic insert device. A precision flow regulator, set to a flow rate of 50 to 100 milliliters per minute, is used for fine control of the delivered gas. Making sure the precision flow regulator is closed, open the tank top regulator first, followed by the precision regulator. Reduce the flow rate to between 10 to 20 milliliters per minute after 15 minutes to avoid creating bubbles in the water. Watch the flow rate value closely over the next hour and make adjustments as needed, since the pressure drop will change while the system equilibrates, altering the flow rate. To capture images of the plate and Foxy sensors, a fluorescence-equipped Olympus IX71 microscope, a charge-coupled device camera from Q Imaging Retiga SRV, and Metamorph image acquisition software are used. The microscope is equipped with an Olympus 31020, a Foxy-compatible fluorescent filter with an excitation wavelength of 475 nanometers and emission wavelength of 600 nanometers. To test for equilibration time and extent of oxygenation for the device, choose 3 points on the Foxy slide in which to measure the oxygen concentration. Capture an image of the slide immediately before starting the flow of gas. Capture images in intervals of 10 seconds over 30 minutes as the gas flows through the device. To test for heterogeneity in oxygen delivery, establish multiple points at 1 mm intervals spanning the width of the channel and measure the oxygen concentration at the well surface. Using Metamorph, export the mean image intensity for each position and plot oxygenation concentration as dependent on fluorescence intensity. Generate a calibration curve by fitting linear curves to the 0 to 10% line and 10 to 21% line, relating fluorescence intensity to oxygen concentration for each position measured. Raw intensity data can be exported from Metamorph and analyzed further with Microsoft Excel or other statistical software. Once the device has been calibrated, experiments such as wound healing assays can commence. Autoclave the calibrated insert at 121 degrees Celsius for 15 minutes within 24 hours prior to the experiment, and work with it in a laminar flow culture hood to prevent subsequent contamination. Soak the sterilized PDMS insert in serum-free medium for 24 hours to inhibit gas bubbles when inserting into the plate wells. Culture MDCK cells or other adherent cells to 100% confluency in a 6-well plate. Create straight scratches in the monolayers with a P200 pipette tip. The scratches simulate wounds in the adherent monolayer. Aspirate the cell media without disturbing the monolayer and rinse with 5 milliliters of media. Aspirate again and refill the wells with 3 milliliters of serum-free medium. Gently insert the device into the plate, making sure to avoid bubbles. Angling the device during insertion helps to expel bubbles out one side. Be careful to avoid putting excess pressure on the device, which could deform the PDMS enough to crush the underlying cells. Place the plate and the device onto a 37 degrees Celsius heated microscope stage and connect tubing from the source gas tank to the inlet and outlet ports of the device. The culture incubator should have a hole to permit tubing entry, and the tubing should be connected after placing the device into the incubator. Follow the same procedure for starting the flow of gas as described previously. To assess wound healing, capture time-lapse images of the cells every 20 minutes for 15 to 18 hours using equipment and imaging software as described previously. T_scratch, a wound measuring algorithm, can be used to analyze the unhealed surface area. After a desired experimental duration, stop gas flow, remove the plate, and proceed to further cell processing if desired. The hypoxic insert device requires less than 2 minutes to stabilize to 0.5% oxygen, as shown here. The device membrane well bottom gap size was a critical factor in determining equilibration efficiency, with larger gap sizes requiring more time to reach steady-state oxygen concentration values. The device also permits a great deal of control over the spatial oxygenation in a single well, allowing the formation of multiple conditions and even generating a cyclic oxygen profile across the surface of the well. MDCK cell monolayers were exposed to 10% or 21% oxygen, and the surface area of the wound was analyzed over time using MATLAB T-Scratch wound healing algorithm. After 11 hours out of 17 total hours, 6.87% of the original wound remained when exposed to 10% oxygen, while 64.4% of the wound remained under 21%. As shown here, oxygen concentrations are negatively correlated with wound open area for both oxygen concentrations for the duration of the experiment.
We've just shown you how to fabricate, validate, and utilize the hypoxic insert device for a scratch wound healing assay. The device offers a number of advantages over other oxygenation systems, such as a smaller lab footprint and far greater control over the spatial and temporal oxygenation at the cell surface. The device can be utilized by virtually any lab that studies the effect of oxygen or other gases like carbon dioxide on in vitro cell cultures.
When doing this procedure, it's important to soak the sterilized device in culture media overnight to minimize the bubble formation during the experiment. In addition, allow the system to equilibrate before starting the experiment. This is because the flow rate changes as the pressure in the system equilibrates.
So that's it. Thanks for watching and good luck with your experiments.